Sure, and thank you for the audience. Thank you for attending. So today's title is Verifiably Safe Machine Learning in Cyber Physical Systems. So, but I think about it with the breadth of audience, probably the more useful thing is not to reproduce some technical details in the paper, but rather share what I know, what really helps me to be more successful. So for historical reasons, my undergrad starts when I'm 28. I never make to the top of the class. Yeah, I'm not the top tier, but I never make into the top tier class. But looking back, what I find is although I start doing my academic study very late, actually it's very late, I think I have good intelligence, but certainly not as genius or even better. So I think I belong to the reasonably intelligent group, just like you. And the success mostly is, I think, I'm doing the right thing. And I want to share with you what guides me to do what I have done. So on that note, I will get it started. First thing I want to say is what I describe is not what I do it alone. Far from it. So, and there's so many people have contributed to the topic, at least here. So I want to take these opportunities to recognize it. Many people knows we did, or we generalized the rate monitoring scheduling, RMS. So we call it generalized rate monitoring scheduling. And there are 3 persons really makes a crucial contribution. That's Professor John Lahosky, Professor Raj Kumar, and Mark Klein. Actually, when we are being considered to have the IEEE Simon Ramos Award, I recommend to add Mark Klein's name. Yeah, Mark Klein is not a researcher, but he is instrumental. And so is Doug Locke. You know, Doug Locke helps me a great deal. But let's say, in terms of putting this theory into practice, Mark actually led the textbook or the handbook of how to use it in real problems. Unfortunately, the award committee said they limit the list to 3. So who do you want to draw? That makes me in an impossible situation. But I would want to take this opportunity to recognize him. He should have shared the medal, in my opinion. So, and then there's a piece of work called single core equivalence. It's an approach to solve the multi-core real-time computing problem. Because this solution has to go through certification, which is a very rigorous process and requires enormous details, which I don't have. So I organized a very large team. I would say at both academia side. I have a Professor Marco Cancamo. The rest, they're all professors, but they were actually grad students at UIUC. There's Ronaldo, Mancuso, Rudolph, Pelissoni, Hee-Chung Yang, Jung-Won Kim, and Man-Ki Yung. In the industry, we have Lotso Gary, Dennis Perlman, Aaron Dell, Richard Bradford. Though they are key players in the aerospace industry. If you look them up, you will find they're very senior people. That actually is the key for the solution, actually useful and become a reference architecture for what FAA want to do, called robust partitioning. Then we are working on physics regulated AI now. Professor Yangbing Mao, Professor Marco Cancamo, and PhD candidate Hongpan Chao want to for their contribution. And robust perception and fault tolerance. Simon Yu, a student, my student, and Professor Han Xiao. Perception and synergistic simplex architecture. Actually, the PhD candidate Ayush makes enormous contribution. And safe AI-enabled medical guidance system. Sean Song, Manasa Setsana, Professor Qixing Wen, Professor Su Chao Yao, and Professor Gregory Russo. I don't have time to talk about that, to fit this one in. So I skipped it. I tried to fit in and then I find it's too long. So finally, I always forever grateful to Professor John Lahosky, my mentor, collaborator, and friend. I will say the things you're going to hear will not happen without them and many others. So my talk consists two parts. Part one is the methodology that drives my research. My methodology has several dimensions. This talk covers how to select research problems and form a team. These focus on what problem we should really spend time on and how to create a team actually has high feasibility of solving a problem. I would say the skills in this dimension eventually led me to be elected to the necessary advisory council's aeronautic committee. Most of them are aeronautic engineers. I'm in kind of an exception, come from embedded computing system, not an aeronautic engineer. So I always said that able to figure out what is the really critical problem to solve, and then organize a team capable to solve it is a very important skill. Now, there are several more specific things, events I want to talk about. How this methodology steer us towards the right direction, even we start with a wrong direction. So the first one is in our early days research in real-time scheduling. We try to using EDF, I will talk about more, and then
Professor Shah, sorry to interrupt. The audience asked whether you can put your presentation in the full screen mode, the presentation mode. Thanks.
Thank you.
Thank you very much.
Then sort of the one thing is we pick the quote-unquote inferior baseline, the rate monotonic. The schedulability is only 68% according to Lu and Lillian paper. We use rate monotonic rather than the 100% EDF as the baseline. That pivot eventually let us transform the real-time computing theory, standard, and practice, and finally led to the IEEE Simon-Ramos method. That means we start off from a wrong direction, and we correct our research direction early on, and what makes us to avoid walking down the unproductive dimension. That's what I want to talk about. Another way is when the schedulability analysis theory failed in the real world, then I look into that. Why it failed? It turns out it's not a logical error. It's a completeness problem. There are certain dimensions of the problem was not basically a necessary requirement are not being addressed by the original fail. That is a real-time synchronization. And then the solution. Then eventually led to the test of time award. And then when FAA allowed we on a software to use only one core in a multi-core chip, at that time, it's already 8 core. If you buy 8 core chip, it's still only allowed to use one of them. And then the solution needs to go through the certification process, which is way beyond my expertise, the certification. But it's such a challenge led me to create a team and finally create a reference architecture and certification guidelines for multi-core real-time computing. Actually, is in use and avoids this quote-unquote crisis. So the part 2, I want to talk about the verifiable safe machine learning in CPS. I want to talk about AI's hallucination gene and what it takes to ensure the safety. I want to talk about older solutions, simplex architecture, and its extensions. Why I believe that it is a good solution approach, which includes teaching physics to deep reinforcement learning to reduce the hallucination probability and the deep reinforcement learning simplex, the DRL simplex architecture, for the containment of reinforcement learning hallucination, and also potential AI software bugs. I will the last thing I will talk today is perception simplex, built upon verifiable safe solutions for obstacle detection for collision avoidance. And then we are working on synergistic simplex, the integration of perception and control so that we can get end-to-end safety. But it's not ready. I wouldn't say it's ready. So I won't talk about it. And there's a topic very close to my heart. I work on it for a decade now. It's verifiably safe medical guidance system for sepsis. And also the use of AI safely in medical. What really holds it back is if you see the AI recommendation for treatment, actually, statistically, they're very, very good. They can take exams and score very high. Except every now and then, they give crazy recommendations, completely out of the wall, the hallucination. So no physician would use it. There's two problems. One is if physician listen to it, physician has the liability, and the AI cannot explain why it work. And sometimes it just give you off the wall recommendation. So again, it's the safety issue. Actually, I hope that our community can pay more attention on this problem. So I will talk about the research methodology. The first thing is we want to focus on the intersection of these three dimensions. We need to know our capability and leadership skills, the ability to form a dream team who share a vision and have complementary skills. And then we also need to know what are the critical technology bottlenecks in the major trends in research and development. For example, the major trend now is AI. Many of those problems are so big. It's unlikely any of us alone can solve it comprehensively. So we need to form a dream team. Basically, dream the same dream. So what is my dream? What's your dream? What are the dreams of my students? What are the dreams of my colleagues? And many person probably working in industry. So what are the dreams of your supervisors? We have to find a common ground. And then we need to know our strength and weakness, and then able to find a common dream. And we need to recognize the role played by our colleagues. Oh, also, I want to mention one name in the audience. If you saw the name of Doug Locke, we both did the PhD together at CMU, but I get the standard stipend. Doug Locke actually had a full salary from IBM to do his PhD. So you know, he is a very, very different, let's say, student, really different student. I want to say I learned so much from him because I just began to learn a real-time embedded system. But he is a highly accomplished engineer, and we work together. And I would say without him, I don't think I can do what I'm doing now. So Doug, I just want to thank you again.
You're too kind.
Okay. So the next thing is I'm a system engineer in CPS. So I won't say this is for every, I won't say this will good for mathematical theory or things like that. Let's say just from the CPS system perspective. So what we need to do is focus on newer challenges, inspire the research. You see the chart. That chart comes from the National Science Foundation's commission to look at the history. It said, what is the best way to maximize the success in NSF funding. So the conclusion is there are at least 3 ways to be very successful, but there is a recommended best approach. The first one is a pure basic research. Will it work? Of course. There are many highly accomplished persons, like a Niels Bohr in atomic physics. And then we have Thomas Edison. He organized this research lab and accomplished so much, from lightning to the electricity or electrical motor. Okay, he's being eclipsed by Tesla's alternative current, and which is supported by Westinghouse. But that said, he's still the first guy to get, the light up in a segment of New York City. He invented the movies, the recorders, right, sound recorders. He invented so much, and he never really paid much attention to why things work. So you have one dimension is really pursue the fundamental understanding of the nature. Another one is solving the pressing technological problem the society wants. They are all great. They're all great persons. But Pasteur actually is the role model. And in fact, I want to mention that Dr. Charles West, V-E-S-T, not W-E-S-T, was a most successful former president of MIT, and he is a subscriber of this Pasteur's theory. He said, this is what MIT should do. Put one foot in the fundamental basic research and put another foot on problems have large society impact. And he later on being elected to be the president of the Academy of Science, and he gave many, many talks about why this Pasteur's approach is preferred approach. It does not mean you cannot succeed in other ways, but that is the, say, optimum or near optimum way. So to me, if it's good enough for running the MIT, it's good enough running the US Academy of Science, probably, and I should say yes, good enough for me to follow. So yes, I will recommend it. Actually, there's a book. You can get it downloaded for free. So you look at some examples. They call use-inspired research. I change in one word. I say probably more accurate is real-world challenge-inspired basic research. Louis Pasteur asked the question, what causes infectious disease and how to control it? He also asked more mundane question, what makes the meal turn sour? So we have a pasteurization of meal, right? Even we use it today. So he said, it is the bacteria, and he started the revolution called microbiology. And then in semiconductor and superconducting, John Bardeen was in the AT&T lab. The early computer using the vacuum tube is so unreliable and so inefficient. Can we replace with a solid state devices? So he wanted to investigate what law governs the flow of currents in semiconductor so that we can make a transistor. He did make it and demonstrate it. Without that, we don't have we owe our career to John Bardeen. And then he questioned, what makes the superconducting possible? That gives the first theory in superconducting. I will say a few words, which is very inspiring to me. You know, John Bardeen later on joined UIUC and become a professor. I didn't have the opportunity to meet him, but I did know his academic grandson, Professor Prof. So I asked, did you have a chance to study under Professor Bardeen? He said, no, he's already retired, but he come back to lab very often. I said, hey, you are experimentalist, but Professor Bardeen is a theorist. Is that his students are mostly theoreticians? He said, no, the majority of his students are experimentalists. I said, I don't understand. And he said, that's why you are not John Bardeen. He laughed. He said, there are too many ways for you to hypothesize in physics. You never get it done. So what he wants to see is to hire the truly outstanding experimenters to identify and measure the unusual but high impact phenomena. Let's say, when superconducting will occur, under what conditions, and what are all the measurements, so that by studying those truly important real-world phenomena, he can make a theory of superconducting. And before he make a theory for semiconductors, and he got 2 Nobel Prizes. So focus on the true high impact real-world problems is a good idea. And if we look at computer science, essentially Alan Turing are being asked, how can you crack the Nazis' enigmatic code? And he make the machine, now we call it computer, and he did it, and along with the theory. So extend or create new theory or new technologies to solve the problem cannot be solved by existing theory is the way to go. That's my summary. Now, we may not be able to accomplish as much, but I think that's the right direction. So I will talk quickly about 6 cases of what I actually have done that. No, not theoretical, but a personal experience. So here's the free real is my summary. Actually, the free real summary is also inspired by a talk by Professor Jiawei Han in my class called How to Improve Your Research Skill. And Xue also, Professor Liu Xue also give a similar talk, very inspiring talk. I say, Xue, thank you for your talk. I always recommend the student to study your experience and insight.
Thank you. It was my pleasure. Thank you for inviting me.
So he said, I said, hey, Han, can you summarize your talk? And then he thought about it. He said, my talk is 3 hours. Real problem, real data, real solution. Yeah, his talk is very long. If you mourn his talk, how to be successful in data mining, he gives 3 talks. So I all record. I should have all the slides. but he summarizes in this real problem, real data, real solution. So I think, that actually is a good summary. I'm not doing big data, but the 3R nomenclature still works. I would say real world problem that cannot be solved by the application of existing knowledge. So you're not just a clever application of the existing knowledge or theory. Real world solutions. The solution can be demonstrated in real world setting so that you cannot omit anything which is essential. And then if we are in system engineering, then you want to make real world infrastructure changes for the new technology. The new technology may not be compatible with some essential requirements, like the IEEE standard at the time. The GRMS scheduling is hopeless. Nobody would in industry use it if the standards are not changed. And changing IEEE standard takes 70% supermajority. And I did it. If somebody want to know how I did it, I'll discuss it. But I don't think I have time to cover it. But I will use the simpler case of the single core equivalence set. How can you go the way? You have a solution. If a solution is truly innovative, it's likely to be incompatible with the existing, let's say, operating system, and behind the operating system are IEEE standard. So you have to go all the way. That also means how important is to form a team. There's no chance me alone or even a few academic friends can get 70% supermajority vote to change IEEE standard. Just don't stand a chance. All right, so now I talk about 5 cases in a bit more detail. I think I mentioned that, but let's go to detail. The time is short. Liu and Leiren wrote the seminal paper on real-time scheduling. Under the assumption that all tasks are independent and periodic, he proved that EDF schedule earliest deadline first schedulability is 100%. Rate-mounted schedulability is roughly 68%. Certainly, as an academic, we say, well, EDF is A+. Rate-mounted scheduling, maybe C, right? Pass. But unimpressive. So in the early days of the real-time system initiative program, the real-time community want to extend or generalize the Liu and Leiren seminal work, such as scheduling aperiodic tasks, handling task synchronization, so on and so forth. A bunch of important details has not addressed by Liu and Leiren. Now, since EDF is 100%, rate monotonic scheduling is 68%. Clearly, we should build our foundation on this 100% instead of the inferior foundation, only RMS, only 68%. That seems is very intuitive, and we fall into the trap. And a lot of friends, somehow they stick with EDF to the bitter end. I'm not saying it's totally useless, but does not solve a lot of practical engineering issues. I will say why. We initially picked EDF the baseline, but soon pivot to the quote-unquote inferior rate monotonic scheduling. So what make us to make the fundamental change? Since I'm working on hard deadline, like avionics software, it is safety critical, and it has to be certified. And in safety certification, there are 5 levels. That's a diagram on the right. Level A, catastrophic, like a flight control. You lost it, you lost the plane, people will die, and plane will crash. And then B, C, D, E, okay. I won't go to that. So the important thing in the certification is this. Higher criticality tasks shall be certified to be schedulable from timing certification, even if the lower critical level tasks fail arbitrarily, for example, overrun, or go to infinity loop, or whatever it does, pieces. So that means the higher critical level tasks, such as a flight control, should be run and not even hindered by the fail of like a mission management. Let's say, how can you stick to the route originally planned? Now, under EDF, those violation of the certification requirement is unavoidable because the rate monitoring assignment is static. So all the jobs are same priority. So in principle, you can make all the safety critical tasks has higher priority. But doing so has some practical problems. What if the safety critical task has a long period or lower rate? But those are solvable problems. But for EDF, the problem is fundamental because a low criticality job, when you get closer deadline, you need to give a higher priority. So therefore, you can never certify the safety critical task set independent of whatever happens in the lower priority. You always have to take the interference into account. That means you need the certification itself is endless. When a low level, you need to do combinatory certification and people won't even touch it. So did I know this 5 level? Of course, I was a new PhD. But I'm a humble person. So actually we get a grant from IBM Manassas. So Pat Watson was the program manager or a grant manager. I always worry about we don't understand the real problem. So I decide to pay a visit. I tell them the list of things. And Pat said, hey, Louis, there's something I didn't think we asked you to do. Well, our software needs to be certified. And we want to make sure that we can certify the safety critical software, the flight control, and without even know what the lower levels in mission control do or would not do. We can, so such that we can move on for good. It's certified, it's certified. Whatever changes you are done for the lower level, I don't need to know. You remain to be certified. And look at that, think about it, it's clear. Either I just have fun, do the EDF thing, or if I want to solve a real world problem, I have to pivot. So we pivot. So under rate monitoring scheduling, we can ensure that jobs of high criticality always have higher priority and consistent with rate monitoring. We can raise long period task priority by doing period transformations. Essentially, you do a automatic task slicing. So let's say you have 10 milliseconds, over 100 milliseconds, 100 milliseconds give you low priority, then you slice it into two tasks. So now your period becomes 50 milliseconds. In the first half, you do 25, say do 5, in next do 5. So you still, well, have the same job, but you execute it in 2 pieces. And it turns out you can do it automatically. You don't need to do the manual slicing. This way allow you move a task priority up and down, and consistent with rate monotonic scheduling and consistent with the criticality ordering. So you can get the rate monotonic priority and the criticality order completely consistent with a few some simple work and even automate. And then, of course, what about 68%? It's not good, too low. So we recognize that we need to replace the low NNM bind by excess schedulability analysis. Actually, that work was led by Professor John Lachowski, and which became a Information Paper Award. And then I want to add another thing is period transformation can also improve the schedulability because the residual between 2 periods, let's say the long divided by the short, the size of residual correlates positively with the schedulability. If the residual is 0, that means you get harmonic task, then rate monotonic is 100%. So there are other tricks to beef up the rate monotonic scheduling. So also, whatever cannot be used by the rate monotonic can be used by non-real-time tasks. So just separate the priority into 2 classes, real-time priority and non-real-time class. So nothing is waste. So since the general operating system, like in Linux, the normal version, and the Windows, that's what they do. The default is rate monotonic, have 2-class priority, and the real-time tasks are usually audio videos, are far from getting 100%. They have 20 or 30%. So, and the rest are non-real-time. So you can still use the processor effectively. So this makes also the wide adoption of GRMS in practice. So this example says that it's important to know all the critical requirements. If we don't know the critical requirements, we might walk down a path. We never see the daylight. So sometimes a theory early, everything is correct, but the quote-unquote correct actually makes some unrealistic assumptions. So that is different from a theory which has logical errors. That rather a theory which is incomplete. Okay, so the early theory included exact scheduling are incomplete. It did not really properly account for the synchronization delay. Okay, so, but anyway, people will start using it, maybe under my influence or good or bad, people are trying it. And then finally say it didn't work. So to be very specific, it's during the early days of the programming language called Ada. It was reported that the task missed the deadline. Even that workload is way below the Liu and Leland bound. Or even you're adding the critical section length, right? You delay by critical section length. So you just brute force add all the If you share a log with somebody else, you just add their critical section length into it. Now that's not a correct algorithm, but let's say in ballpark it's correct. But you found you still miss the deadline, even you account for all the length for lower prioritized critical sections. You can't add it into all. Sometimes you still miss that deadline. So it's kind of mysterious. So the results get there's something wrong. Actually, the more correct is there's something missing in the schedule brief theory at the time. So I like to know what happens in the real world. So I asked for samples. They're complicated. It's so complicated. It's hard to develop any theory or improvement. So I said, what should I do? Then I remember a lessons in the history of science. It's called Occam's razor. The American way to say it is, keep it simple, stupid. That is the impolite way of saying it. So basically the question is, can we construct the simplest task set which also embodies such a phenomenon? You don't want to have the most complicated data set or the quote-unquote real-world data set, because it's hard to form hypothesis and validation. So instead, you want to reduce and create a model problem, which is as simple as possible, but still you have the same behaviors. And then you put it back into the real world and see if it holds. Now, in today's world, you can say a theoretical pre-training or pre-modeling. So after some effort, I found I only need 3 tasks to create such phenomena, and then I call it priority inversion. So basically, a lower priority task locks a mutex, but a high priority task arrives and try to lock it, and of course, you'll be thrown into the wait queue on that mutex. So as the low priority task continue its execution on its critical section, a medium priority task comes in and say, hey, I don't need any shared data. Then the OS say, okay, medium and low, I will dispatch the medium. So the waiting time is not bound by the length of critical section. So I call it unbound priority inversion, means not bound by the length of critical sections, the waiting time or the blocking time. And then later on, to keep it simple, we just call it unbound priority inversion. And that actually is an example used in the paper. Okay, so one lesson is actually when we're doing this AI thing, we also do the same thing to find the simplest construction, which allow us to observe certain success or failed behavior. That actually is what John Bardeen or Isaac Newton did. He wanted to understand the general gravity, the K times M1, M2 divided by R squared, right? The famous universal gravity theorem. What did he do? Well, he had 2 heavy metal balls being handed down from a church. Right? He didn't go to the moon or something, or go to the star. He found the simplest thing which embodies the phenomenon. That actually is the right approach. So, and then you go back to the complex world to validate. And okay, so anyway, once we have this isolated, simple problem, then the solution is clear. So we have this priority inheritance protocol. Hey, say if I borrow a high priority task, I just borrow his priority and get out of the way and execute my critical section and get out of the way. So that is the first workable solution. But the worst situation in real-time scheduling is a system with synchronization is getting to a deadlock. That guarantees missing all the deadline under the sun. So we need to solve the deadlock problem. So as a system engineer, before we rush out and get something new, we want to look around and say, is anything we already in use? We can reuse it with some extension, such that you can keep the complexity of the system low. You don't want to have assembled a lot of unnecessary redundant capabilities in the system. You want the system simple and effective. So that really means you need to look into your system again. It's the same similar thing beside the instruction set. You don't want a lot of redundancy. So we all know that if the logs are acquired in an acyclical order, there will be no deadlock. You need a cycle to have a deadlock. And the rate monotone priority is static, and there's no cycle in it. Can we just let a higher priority task log another unlock the log? Isn't that we go high priority? Not exactly, because the priority inheritance spoils it. Later on, a task priority is no longer fixed because it can inherit, it can go higher to some level. You say, okay, that's easy to solve. I just make sure every task, a new task want to acquire log, has priority higher than the maximum priorities all the tasks can inherit. So this way, we still have a cyclic order, a total ordering. All right, then how to implement it? Oh, why don't we register how high a task priority can be raised onto the semaphore it uses. So here we figure out the priority shifting protocol. Okay, so that's the story about this test of the time award. The two lessons is for a complex phenomenon, you want to create a different task set, the simpler task set possible, but it have the similar behavior. The second is, before you rush out and buy or import something new, look around and see whether or not you can build on something you already have to keep the system simple. It turns out that gave us that paper. How do you think about it? Oh, that's how we think about it. So I will talk a little bit about this. How much time do I left?
I think we have roughly like 15 minutes or 20 minutes.
I will go faster.
Yeah, because we wanted to save some minutes for the attendees, right? So they may have some questions for you. So
okay, so I will go faster. Thank you.
Yeah,
I'll go faster. So basically, we notice a phenomenon. FAA allows only to use one core per multi-core chip until the inter-core interference problem was solved. To be specific, the statement is all the interference channel shall be identified and the interference are bound and accounted for. All, not just some. Basically, you want to get rid of all the uncontrolled sharing of resource shared by all the cores in them. So this is an architecture-dependent task and requires a very detailed knowledge on low-level architecture, what protocol the designer does, how can we partition the resource such that the partition of different resources can work coherently end to end. So this problem is what I say, it's conceptually simple, but extremely hard to get it right. And then you want to do it in a way that's certifiable or has good chance being certified. So realize my own limitations. So I organize international collaborations between university, research labs, and the avionics industries. And in addition to publications, we produce actually it's at the time was an internal document, but now everybody knows it, if they actually in the industry. So I would just click this one. So I'm not going inside. So I just want to see, when you have a problem at that scale, you really need active participation. You cannot get everybody agree, but you need a critical mass. So the universities, we have Rockwell Collins, they actually building avionics, that's there. And then we have Lockheed Martin, they are aero company. And we have Wind River, they build a real-time operating system for NASA and a lot of aerospace. We have Jane Bay and Alan Burns, they are colleagues in York, University of York. And then we have folks, Stewart Allen, he's the British firm, BAE Electronic Systems. And we have actually our colleague Stanley, his colleague, Derek Kingston, Matthew Clark. They are actually with the Air Force Research Lab. And we have colleagues, Tae-Ho Kim and Woon-Ji Park. They are actually a government research lab in South Korea. So, so also you can see that there's acknowledgement. These early versions have been sent to Michael DeVore for review. So who's Michael DeVore? He's the certification chief of FAA. I know him because both of us serve on the academic science committee on dependable software, certifiably dependent software. So we know each other. He said, I said, because of my job, I cannot endorse any research. But if you have anything wrong, I will let you know the minute you send it to me. So he's a pure negative feedback. And that is a variable because he is the software certification chief for the FAA. So yeah, this you can look at document, won't go into it. So this first page, I bring it out, is to show that a lot of problems we cannot solve it alone. We want to cultivate a network of engineers across academia, industry, and government organizations such as FAA. That's why building a team is so important. Now I will say a few words about this AI thing. So the first thing is to fix any problem, we need to know the root cause. Upon investigation, we first need to decide what it takes to certify a system, verify a system, and then whether or not the technology in question is possible, can meet the requirement, or if there's something fundamentally wrong. So challenges in certifying the safety of AI-enabled CPS, just like anything, to ensure safety, certification requires one, an analytic model for the system behavior. with proof of safety properties. 2, verification and validation of the software implementation. The AI software failed on both of these accounts in terms of control. The coverage of software is hard to measure or fulfill. There are millions of tunable variables. And if you want to certify, each time you run and learn something new, you need to recertify. Basically, the certification safety survey is either impossible or impractical. Now, the problem becomes worse. It's not just the software complexity problem. The root cause is AI's use of non-causal statistical method to approximate the causal deterministic relations in Newtonian physics. For example, the Markovian decision process is the foundation of deep reinforcement learning for control. Now, when you using probability distribution to approximate fundamentals like energy conservation, momentum conservation, or even F equal to ma, you always suffered from the long tail effect. That means no amount of training can get rid of inconsistency. You can reduce the probability, but you cannot make it come to zero. So therefore, the hallucination or generating output inconsistent with the law of the physics is in the gene or in the DNA of reinforcement learning. There's no way to get around with it until it abandoned using statistical model to approximate deterministic relationship. All right. So hallucination is something we need to deal with. That cannot be removed. So therefore, hallucination containment is the only viable solution. So our goal is to achieve verifiable safety under the assumptions of, well, we have a functioning electromechanical system, a functioning computing platform, and lawful behaviors of other vehicles. Actually, there's some specification. Let's keep it simple. When you cross the green line, nobody will run the red light and T-bone your car. All right. It's hard to guarantee safety if somebody just ignore the red light completely. All right, so we do have certain assumptions. The safeties are conditional. Under those conditions, we can prove the safety. The second part of the last part is not only the algorithm, but also the software implementation complexity matters. Hey, the algorithm is right, but the software may be impossible to VMB. That wouldn't work either. So we need to handle both. So from a system engineering perspective, we divide a safety level of several gene cars and trains in 2 levels. First is safety level. The level 1A is collision avoidance, because that could cause loss of life, the destruction of property. Level 1B is you're speeding, you didn't stop on stop sign and so forth. The traffic law violation. This is statistical, but we can determine guarantee is the obstacle detection and then collision avoidance. We'll talk about that. The level 2 is you drive in the right place. That is mission management. We won't talk about that in this talk. Okay, so we'll focus on the issues in the level 1A. So it turns out an old technology, actually, this one actually just happens. I developed mostly on my own. That is a closed domain solution. So basically, can we verifiably have verified correct fault tolerance of complex software? That turns out, is an unavoidable, unsolvable problem with the domain of software fault tolerance. Why? People did propose inversion programming. So you have the same set requirement, you ask 3 teams, develop 3 versions, and hopefully all the fails are uncorrelated, so you can take a voting. But it turns out this intuition is mathematically incorrect. Inversion programming actually makes system less reliable than just put all your resource to do a single version. Actually, unless you get diversity for free. But if you want to develop a program, actually you're worse before. So it sounds like a total total rebellion against the damn popular inversion programming. So when I try to publish it, a lot of people say reject it, but I show them the math. That's not clear. I rewrite that. So anyway, after more than a year, the review committee being to expand twice. And then finally, I not only published, or also become the sort of the highlight of the month of the paper. So you can see the proof in my paper called Using Simplicity to Control Complexity. That actually review paper succinctly makes the mathematical case and why you want to use simplex architecture instead of inversion programming. Basically, you make one version, do the minimum one, but it's verifiably safe. And then you create a safety envelope, and then run the complex software. Yeah. Okay, so if you look at the right-hand side, you look at the diagram, you see a complex controller, a safety controller, some controller is simple enough. You can actually get the certification, or you can do all the VMV. So you create a safety envelope, and then it was called recovery region. Essentially is that if the complex software, AI or otherwise, make a mistake, then you can always take over by the safety controller and then recover from it and never left the ellipsoid. That's the legal point of function. This lines just pictorial notions about safety constraints. So you want the system not only safe, but not only stable, but also satisfy for all the safety constraints. Why that safety constraint is important? Because you can keep things totally stable, and then run the red light, right? So is running the red light safe? Absolutely not. Can you run the red light stably? Of course you could. So stability, and the stability region or the recovery region are inside the safety constraints. We call such an envelope the safety envelope. So a safety envelope is a stability envelope meet the safety constraints. So once we have such a safety constraint, so it turns out there's a fundamental trade-off between agility and stability. So the safety controller maximized for stability, so you can get a larger envelope, and complex controller, you maximize the performance. Basically, is you can follow the reference trajectory very closely. So let it run unless you get too close to the safety boundary. and then you take it over. So that was the old simplex architecture, and it's because the many success of simplex architecture in aerospace industry. So eventually, I become a senior person in the industry, and also my skill in finding right problems and organize teams, together with my success in the scheduling and the simplex, led to the election of me into the NASA Advisory Council. So still, even we can make it safe. Essentially, the simpler solution, which we will tell you soon, is there's have some limitations we need to remove. But let's say you can just replace the complex controller with the reinforced learning. You can guarantee safety, but there are some limitation I will talk about in the next chart. But still, each time the DRL fail, you switch over. By definition, you switch to a safe but low performance, and you have a disturbance. So although we cannot eliminate the hallucination, we want to suppress it or reduce it to the lowest possible, and with minimum training using physics. So we design, quote unquote, to teach physics to the reinforced learning. The first thing is we put the Pointer function as a penalty function into the reward function. The Pointer function works if the value actually go quadratically higher when you away from the set point or the reference trajectory. The further you're away, then the reward function will be larger, actually square larger. So it's quadratically larger. So you will really teach the reinforcement learning, say, hey, don't get too close to the edge, because whenever you get to edge, you get a penalty, which is quadratically larger and larger. So you will learn actually stay out from the boundary of the stability envelope. The second thing is, so that's basically the stability envelope, like usually is actually is in the form ellipsoid. This is a two-dimensional plot. Let's say x and x dot. So it's an ellipsoid. We want to focus a sample around the boundary, because that's where the likelihood of the system fail. So this actually is a special case of the inverted pendulum. We do also embed a lot of physics computation external to it. I just want to make a simple thing, like there's something called sine theta, cosine theta, right? If you just ask the AI, say, tell me what is sine theta, what's tangent theta? Oh, it's a big job. And you can train it for days and nights. It still at low resolution. So certain computation is a fundamentally, let's say, the AI is computationally challenged. So you don't want to burden it to do those things. So you want to embed like the energy, you want to embed all the physics expressions and augment the input vector. And then we want to edit the lane, because certain things say you have a energy conservation. So don't let them edit the lane. Say if you say A equal to B, which is known to be is to be preserved, don't let it ever edit it. You disable the attenuated function, things like that. So you preserve the physics identity. Otherwise, some noise in your sample, it will let you create energy or destroy energy. You just run the experiment, you will know. Unless you hard embed the relationship. it will tell you energy will not need to be conserved from time to time. They can emit energy from nothing. So actually at this point, we achieve, at least in the invariant pendulum, we can get 1/10 of the training time, and achieve, let's say, 10x fast to discover the stability region. And also, well, I will mention that Professor Yang Bing Mao and a teacher student Hong Pan Chao actually led the work, and I want to recognize that. I'm kind of more and more interested into a high-level advisor these days. So now we've got about simplex. So if we use the original simplex, that low ellipsoid is a linear robust controller. I should mention that you can replace with L1 activity control, which actually allow you to handle mechanical errors, because mechanically partially fail, let's say an engine lost power. Then the stability envelope will change because the model for the plane changes. The L1 actually can compensate those disturbances of partial fail and restore the envelope. So I want to acknowledge Professor Nara Hoba-Kinyon, and I work out something called L1 simplex, which is very successful in aerospace, because you can keep the envelope working, or even with limited mechanical fails. Okay, so after that, I want to say, let's say there's no mechanical fail for now. Let's go back to the more ideal situation. So that you will see a lot of purple dot. What is the purple dot? The purple dot is when we train this inverted pendulum, what we found that you will do things which is unsafe outside of the safety constraint, those are blue dot outside. But it can also go outside all of the linear controllers stability envelope and return, and with good performance. Let's say, wow, why that's the case? Isn't that we get the largest envelope under this LMI package? That isn't the blue one is the maximum? It's the maximum for a linear controller. And reinforcement learning are non-linear. So it's entitled to have high performance and larger stability region. Except one thing. From time to time, you could hallucinate, and then you have total fail. So now we face a dilemma. The dilemma is this. If we keep the, say, inverted pendulum working inside this blue ellipsoid, it's safe, but you sort of tie its hand. You cannot fully enjoy the higher performance and higher stability region. If you said, all right, you go outside, and if the reinforcement learning go outside of the blue ellipsoid, which is the maximum stability region the linear controller can handle. So if you go outside and hallucinate, well, you fail. You have no recourse. You have no backup. So to solve this problem is our current active research. And then, of course, I remember that the famous statement said, there's no general procedure to create the for a nonlinear systems, the Leopold function. It may exist, but there's no procedure to find it. And in machine learning, which is a lot worse, because you don't know the actual functional form of reinforcement learning. They are hidden inside the latent space. So you cannot submit to MATLAB linear matrix inequality to say, compute it. You say, hey, come on. What's the function? tell me explicitly what's the function which characterize the reinforcement. I don't know. Nobody knows. It's hidden there. So essentially, it sounds it's an impossibility to create a larger envelope to account for the blue dots inside the polygon, but outside the blue thing. Then I think about it. Do I need to solve this problem? Actually, I don't. All I need to do is to do a reverse engineering. So I have all those blue dots outside of the blue envelope, those purple dots, but inside of the polygon. Can I reverse engineer such that I can get a bigger envelope? Then, of course, the bigger envelope has to be hybrid control. It cannot be a single controller. Yeah, sure, hybrid control is just a piecewise linear control. You know? So it's completely verifiable and certifiable. In fact, most airplanes use this hybrid control under the name called game scheduling. So it is well established. So it turns out, although if you give me the inverted pendulum, I cannot draw the safety boundary, safety envelope. But if you show me the blue dot, I can reverse engineer and create a hybrid controllers such that when it fails, when we're outside the blue ellipsoid, we will still able to handle the hallucination. So therefore, we can have certifiable safety again. You say, hey, Louis, why don't you tell me how to do it? Well, it turns out we already work very well for the inverted pendulum, and we tested it on the robot dog. It worked quite well, at least in the case. But we are submitting this as an NSF proposal. So I'm sorry that I cannot disclose how we actually do it. But if you want to work with us and join our proposal, we can discuss that. But at this point, we are in proposal writing stage. So as a preliminary result, I would say actually it's doable. You can reverse engineer. Can it be under what condition you can reverse engineering? How effectively reverse engineering? All those are the research topic we propose to the NSF. Okay, so I already talked about this part. So I want to talk a little bit about the perception simplex goals. Say I want to look at the level 1A, collision avoidance. So to keep it short, is that when the LiDAR beam, the LiDAR beam return, you can work on the geometry questions such that you also know under what basically the string of the return signal tells you at what distance you can really detect the object reliably. So therefore, we can handle partial fault on ring. If the fault's too thick, we drive the roadside and stop. Otherwise, we drive slower because the detectability range will be dropped. So we do have a verifiable analytical way to know the existence of object without AI. So once we have reliable object detection and the algorithm is simple enough, the software can be VMV'd. So we can override the machine perception if you fail to detect an obstacle already detected by LiDAR. This allows the reinforcement learning simplex to keep a safe distance. I want to also mention another thing I think somehow I forgot to put on the slides is the current approach in the perception is violates the a principle in safety engineering, is that it commingles the obstacle detection with obstacle classification. Obstacle detection is level 1A because it's safety critical. If you don't detect it, you might run into it. Classification is not. If you classify a car, let's say Chevy into a Ferrari, or the vice versa, you are wrong, but it's not safety critical. So, okay, so commingle a safety critical with a non-safety critical together in the software. It makes the verification and safety assurance unnecessarily complicated. So thou shall not commingle different criticality software into one package. You want to isolate them and protect them. That's one of the beef we have with the current generation of perception. And we will engineer a way, make sure that wouldn't happen in our version. Now, with those detections, we can do a lot better. We can prioritize the machine learning perception to focus on nearby object first, because the LiDAR obstacle detection runs much faster. So you can say, hey, pay attention to those nearby object has a higher collision risk. And a paper by Clara and a student actually showed that if you can prioritize it, the whole schedulability will be improved greatly. And I think that is a best paper award in one of our TSS between Tarek and his student. But he didn't say, how do you do it? We say that actually we work out the details. LiDAR is one way to guide the machine learning. Certainly help establish a safe driving monitoring zone. Another one is that the LiDAR also will tremendously reduce it allows us to use a much smaller GPU. The reason is essentially with LiDAR's detection plus the AI's classification, we can get the jobs done. And then we can also, actually, all they need to classify are the nearby objects. The far away objects is not of interest because by the time you get close, the car probably will go away a long time. So actually it's 100 or 200 meters in terms of safety. So also that once you classify an object by the machine learning, to track it, you can use LiDAR. When you use a high frequency LiDAR, in fact, that I think running 100 or 200 hertz, you have those time of flight sensors. The car can hardly move more than a meter, or actually more than a 5 centimeter. So the image between the same car's image in two samples largely overlap. Basically, the interception over union is 80 or 90%. So we know it's the same object because it's impossible to have two cars occupy the same space. So therefore, you can classify it once, and then you leave it to the LiDAR. LiDAR software is very efficient. At least we have a version very efficient to keep track of the car, and you don't need to classify again until the image overlap or a new thing comes into the vision. So there's a great synergy actually between the LiDAR, perception, machine learning, and safety. They're great. So now we come to the summary. So first is we want to focus on real-world challenges, know the bottleneck in a major R&D trend. We want real-world solution, address all the essential requirements, not just some. Sometimes you may need to revise the technological infrastructure like the standards or address the certification concerns. Either compliant or there's no shortcut if you want your research actually has a large impact in the real world. And of course, you don't do it alone. That's why building a team is so important. Building a team with a shared vision and sufficient breadth and depth. For example, avionics solutions need certification, but we do not have such expertise. So I organized team. So I already showed you the one chart I put it here, just a reminder. Sometimes you want deep involvement from the experts, actually in the certification community and in the aerospace community to develop a solution are actually useful. So in the current era, I would say AI enabled, CPS, my typo, is verifiable safety. The root cause of AI hallucination is use a non-causal probabilistic model to approximate causal and deterministic relationship in Newtonian physics. So the hallucination can only be reduced, but not eliminated. So hallucination control or containment is really important. And then we should never forget, other than the algorithm, or you want to call it, the AI methodology, also the pure software complexity is too high to be verified and validated for safety applications. That's why we need the containment. To me, the solution approach is to contain the AI algorithm and software force by engineering verifiable, safe operational envelopes in control. I say safe operational envelopes in control and in perception. That is my mantra, is using simplicity to control complexity. The AI is so complex to fully test or verify it or theoretical proof it is too far away. Or I think I doubt even it's possible. Can AI eliminate hallucination? I have some doubt. So to me, the solution approach is the containment and the way we should reduce the AI hallucination by teaching in physics or using physics regulation. I personally think simplex architecture and its extensions are one way to address those concerns, maybe even an effective way. But I would say what I don't think there's any debate is, given evil hallucination, so we need to develop a containment approach, and also we should make use of the physics to reduce the hallucination and deal with the hallucination by containing it. Now, whether or not it should be simplex or other method, that's perfectly fine for me. So on that note, I want to thank you. Questions?
Yes, thanks a lot, thanks a lot, Professor, for the very inspiring talk. Okay, thanks a lot for sharing your great research experience and your current work with us. Okay, I think everyone here, okay, we learn a lot. Since we are a little bit running out of time, okay, so maybe we can pick up like one or two questions from the audience. I'm sure, okay, so if the audience have any questions, okay, they can send an email to you, try to ask your questions. So for the audience, okay, if you have questions for Professor Shah, feel free to unmute yourself. Okay, you can ask a question directly.
Hello.
Yes.
Hello, Professor Shah. Thank you for your insightful talk. And I have a question for the first part of your talk. And I'm a junior PhD student, and I'm very interested in learning more about how to conduct high-impact research. Based on your experiences and lessons shared in your graduate class, what strategies would you recommend for a junior PhD student like me to effectively identify and pursue high-impact research topics?
Well, if you UIUC, I will recommend it. You take my class. The name is called Improve Your Research Skills, which is kind of a alternative class or alternative medicine because it doesn't have a specific research topic. But the faculty does recognize the most important skill in doing PhD is find the right problem, have the right skill to solve it, because the specific change. So I would say I find I give a link earlier, so you can click the link. So I give a fairly long summary discussion about essentially is my take about how to do high impact research. From let me see, I think I somewhere. Oh, I think I forgot to put it in. All right, okay, send me an email. I will send you a link to the summary of their class or my take. And there are many other good talks. For example, Professor Han, Professor Liu Xue, and Professor Y.Y. Xiao, Professor these AI days, Hongji, Han Ji, she's a very accomplished AI expert. And then I have the older generation, like a Professor P.R. Kumar. He now actually in Texas A&M. They hire away him. He's a member of National Academy of Engineering. So I have sort of about 15, and then of course I should say Professor Tarek at the Osaka, and Professor Wickham. Actually he's the LLVM person. He literally revolutionized the compiler field. So many others. So send me a link. I will send you the summary. If you doesn't have enough, then I try to create an account. Or you can even, if you really want to do it, you can remotely attend this class. You don't need to pay the UIUC tuition. You just sit in. So yes, I really personally feel identify problem, building a team, and then how you evaluate what problems are likely to be impactful, how to write a paper. We address all the things, not just with my own experience, but I would say after I listen to Professor Jai Wei Han, listen to Professor Liu Xue, listen to a lot of others, I also steal their idea and put into the summary. Maybe my stealing may not be that good. Maybe you want to look at the original version about how they said doing research. So now, because our classwork, the UIUC does not recommend it. Maybe complete public. Maybe they want to think about, but I can try to create an account for you, so you can look into that. How about that?
Yes. Yeah, thank you very much.
Yeah, thanks a lot, Professor Shah. So I guess we have time for maybe one more question from the audience. Yeah, again, you can unmute yourself. You can ask a question directly. Okay, then I guess we are all digesting Professor Shah's the wonderful talk, right? As we mentioned, right? So if you have any questions regarding Professor Shah's the talk, okay, please feel free to send an email to Prof. And also to answer Marco's question, we are going to we have already recorded the video, and also we are going to do some post processing. And after we get some final checking on the video, we are going to post it on the SIGBED website. We are going to send out the email to everyone, so you should be able to access the video online, hopefully in 1 or 2 weeks. Okay. We will keep you all updated. So with that being said, okay, I wanted to let all the audience, okay, to join me, okay, to thank Prof. Shah, okay, again for his wonderful talk, okay, and also I wanted to mention that, okay, our SIGBED distinguished lecture series will continue. Okay, we are going to have our next lecture will be arranged in the late July, and also we have another one, okay, will be scheduled in November. Okay, so we will keep you posted. Okay. And thanks again for attending this wonderful talk. Okay, and thanks, Prof. Shah, again. Okay,
thank you. Thank you for inviting me. It has been an honor.
It's our great honor to have you here. Okay, to share your experience with us. Okay, for the broad audience, right, from the CPS community. Okay, real-time system and embedded system community. Thanks a lot.
Thanks a lot.
Thank you. So I think we're done, right?
Yeah, I think we are done. Okay, so thanks again, Prof. Shah.
I noticed I have a few typo. Maybe I can send you a version. I understand you cannot change the video, but you can attach it.
Yeah, definitely. Yeah.
Okay.
So if you can send us the final version of your slides, okay. So we can make maybe it's better for us just make a PDF, right? We can also put a PDF on the SIGBED website.
All right. Thank you. Thank you.
Thanks a lot, Prof. Shah.
All right. Bye-bye.
Yeah, and have a great day. Bye.
Bye.